Learn like a pro.
Welcome to our explainer. Today we're going to uncover the invisible fingerprint that's hidden inside every single object. It's the secret that gives each substance its own unique physical identity.
You know, everything around us, from the air we're breathing to a solid block of lead, has its own internal architecture. It's a very specific way its matter is packed into the space it takes up. And if you can understand this packing, well, that's the key to unlocking some really amazing properties of the universe.
So how would you solve a classic mystery like this one? It actually all comes down to a fundamental property that acts like an unforgeable fingerprint for matter, something that makes gold, well, undeniably gold.
All right, let's dive right into our first section and really get to the heart of what this physical fingerprint is all about. So, what is compactness?
At its core, density is really just a measure of physical compactness. It tells us how much stuff, matter is packed into a given space. Just look at the two cubes here. The one on the left, its particles are all spread out, so it has a low density. But the one on the right is just crammed full, making it super high density.
And this simple rule of compactness has a consequence we've all seen a million times. It determines whether something sinks or floats. If it's more compact or denser than the liquid it's in, it sinks. If it's less compact, it floats. See? It all goes back to that packing we were just talking about.
So we have this kind of intuitive idea of compactness. But how do we turn that into a precise scientific tool we can actually use to measure things? Well, let's find out in our next section, the governing formula.
And here it is. This is the master key to everything we've been talking about. This is the governing formula. Density, which we show with the Greek letter rho, is simply the mass of an object divided by its volume. Mass over volume. That's it.
And here's what makes that simple little formula so incredibly powerful. Every pure substance has a unique, fixed density value. Gold will always have the same density. Water will always have the same density. So what does that mean? It means if we can just measure an object's mass and its volume, we can calculate its density and figure out exactly what it is.
Okay, so we've got our formula. But to actually use it, we need to find its inputs, right? Mass and volume. And as we're about to see, that can be a little tricky when we're not dealing with perfect little cubes.
First up, let's talk mass. And there's a really crucial distinction we have to make here. Our formula needs mass, the amount of stuff in an object, not its weight, which is just the pull of gravity on that stuff. Luckily, it's pretty easy to find the mass. We just take the object's weight and divide it by the force of gravity.
Okay, so finding the mass is pretty straightforward. But what about the volume? I mean, for a perfect cube, sure, you just multiply length by width by height. But how many things in the real world are actually perfect cubes? How in the world do you find the volume of an irregular object like a rock?
Well, we solved this with a really clever method called water displacement. You just start with a known volume of water, then you fully submerge the object, and the amount the water level rises, that's exactly equal to the object's volume. It's such a simple but absolutely ingenious solution.
Now let's put it all together with a full example. First, we find the ring's mass from its weight. Then we use our water displacement trick to find its volume. We plug those two numbers into our formula, and bam, there you have it, the final density.
So, we've totally mastered the basics. Now, let's move on and tackle something a little more complex to see just how universal this principle of density really is.
So, check out this challenge. An object made of two different materials. You've got a hollow outer shell with one density and an inner core filled with a substance that has a totally different density. So how do we find the overall density of the whole thing? The strategy here is actually just to break the problem down into smaller pieces. As you can see in the table, we're calculating the mass and volume for each part separately. We figure out the mass of the hollow shell, and then we figure out the mass of the stuff that's filling it.
Once we have the mass of each part, we just add them together to get the total mass. Then we divide that total mass by the total volume of the object. And in this case, that gives us a final combined density of 14.6 grams per cubic centimeter.
And what this whole process reveals is a really powerful and universal principle. The total density of any object, no matter how complex it is always the sum of all its masses divided by the sum of all its volumes. It's a law that holds true for absolutely everything.
And this is really the ultimate takeaway here. It doesn't matter if you have a solid cube, a weirdly shaped rock, or some complex object made of multiple materials. If you can just master finding those two key inputs, total mass and total volume, the fundamental law of compactness will never,
ever fail you.
So this universal law of density acts as a constant, a true fingerprint for any physical object in the universe. And that kind of makes you wonder, doesn't it? What other fingerprints of matter do we rely on every single day without even realizing it?